So today I'm going to go over the ideal gas law and how it relates pressure, temperature, and volume in order to calculate the final temperature of this container with these set parameters, and then we're going to put it in our Google Colaboratory and calculate the final temperature in order to achieve a final pressure of 200,000 pascals. So before we get started, I'm just going to write down what the ideal gas law is. So the ideal gas law is essentially just an equation relating pressure, temperature, and volume. It's a good approximation of the behavior of many gases under certain conditions, but as I will go over in a little bit, there are several limitations that I will go over in the next video, which is when we use the van der Waals equation instead. So essentially we have this container, and we have it's a closed container, and we basically just have some amount of water. We have 1 kilogram of water in here. The volume is cubed, and we are starting at atmospheric pressure in pascals, which is 101,325. And we're starting at room temperature of Kelvin, and then this is our gas constant, which we will have to use in this equation, so PV equals nRT. And so that is what we are going to use to figure out what the final temperature needs to be in order to raise the system up to 200,000 pascals. So that's essentially where we are going with this. So another important concept to go over is partial pressures. So essentially, pretty simple, but the idea is that the total pressure of the mixture of gases is equal to the sum of the partial pressures of each gas itself. So essentially, we can divide this up into the pressure of the air and the pressure of the water, using the Antoine equation. And we can get that pretty easily. And then the partial pressure of the air, we'll solve using the ideal gas law, and then we will add them together to get the total pressure. So the partial pressure of the air is going to equal the number of moles, R times T, divided by total volume minus the volume of the water. So essentially all I did was divide by the volume, and then we need to subtract the volume of the water, which we can calculate pretty easily since we know the mass of the water, and then we can just use our density formula to calculate the volume of the water. But first what we're going to do is calculate the number of moles. So I will write that up here, number equal, and we can essentially just rearrange our equation a little bit, do the initial pressure minus the pressure of the water from the Antoine equation, multiplied by the difference of the volumes, divided by the gas constant times our temperature. So that is what we will use to calculate the number of moles in the vapor phase, which we can then use to calculate the pressure. Okay, so the next thing we need to find is the volume of the liquid water. Right here, I'll do that in green. So in order to do this, we're going to use the density formula. Density, we love density. That's how I always remember it, it's like a heart. Mass over volume. Okay. So density is mass over volume. We know the mass is 1 kilogram, and we know the volume we want to find the volume, we know the density of water, so we can do volume equals the mass over the density. Okay, so the next thing, we're going to use our information in Colab to get all of the hard numbers. We're just going to upload input files that have all of the data for water, like the critical temperature, critical pressure, volume, density, all of that stuff. That way it's just already hard-coded in there and you don't have to change the numbers every time something in the problem changes. So that's what we're going to use for that. So then once we have all of this information, we're going to use our equation and we're going to use a root function in Colab to calculate what the solution will be at this using these parameters. So then what we're going to do is we're going to upload a function called SciPy, or SciPy, we're going to do the SciPy optimized root again, and essentially a root of a function, so we have, our function is going to be pressure versus volume, but if you have any function, essentially, it could just be anything. The roots are where it crossed the x-axis. So this is when the function goes to 0. Essentially, it's just a solution of the function that you can calculate. So it's a means for solving an equation, and we're going to do that in Colab. Alright. So in order to solve these roots, we need to set the functions equal to 0. So we're going to move everything to one side. We're going to move the final pressure over, so we get, these are going to be our final equation, 0 equals negative plus number of moles times R times T divided by the difference of volumes. Okay? So that is what we're going to use to find the final temperature. Now that it's set equal to 0, I just moved the final pressure over so that we can use the root function. And then we need to create a vector in Colab to find the root of. So we'll create a variable called, temperature final equals, and then we'll make a vector, a list of values like that. We can use that to find the final temperature. So essentially what we're doing is comparing the vapor pressure of the water to the final temperature in this vector, and then we will have the partial pressure, of the air. The air equals the number of moles of air times RT divided by, and this is the volume of the vapor phase. And then once we have that, this function will define this function as something, and it's going to return the pressure of the water plus the pressure of the air minus the pressure initial function. We want this to be what goes to 0. And since from our defined function, then it will give us a value for the final temperature. We're going to have to put in initial guesses for root functions in Colab, which I will go over in the next video. But essentially, this is the idea of what we were going to be doing in Colab. We're going to use these formulas to calculate the final temperature given these parameters. Okay, so now that we know kind of what we're doing and we have our formula to calculate the final pressure of the system, we're going to put it in to make a function in our code here, just so that we can calculate what the final temperature would need to be in order to raise the pressure. So in order to do that, I'm just going to import this code that we got in order to get all of the data about, I just make sure it's connected, about certain compounds. That way we can use this file that has all of the parameters on water. So you can look over here. I think it's in here. Data. Yeah, so there's all of these now that we have in here in case you ever needed to change the compound you're using in the system. So for this problem we're just doing water, but you could change, like, so then in here we're gonna add like, we'll type in P. We're going to do the properties of water, because that's what we're doing for this problem. But if you wanted to do, you know, something else, all you have to do is change that, enter, and then it's all loaded in there. So that's pretty helpful. Alright, so the first thing we're going to do is we're just going to define the variables we need for this problem. We're going to have the total volume was 0.01. I'm just going to put the units just so that we know it was in meters cubed. Then we're going to have the mass of the water was 1 kilogram. The initial pressure was 1 atmospheric pressure. We're going to use pascals. The final pressure that we want is 200,000 pascals, and our initial temperature is 298 Kelvin, and then we, what is that? Oh, I forgot. And then we also need our gas constant, which is 8.314 joules per mole. Okay, awesome. All right, so now that we've got all of those loaded up in here, we can put in our equation to calculate the number of moles in the air. So we'll just do N air equals, it's going to be the initial pressure minus the pressure of the water in the vapor phase, which we can get from the Antoine equation, but in this case we're just going to use the properties that we got from this file that we imported. So P dot pressure in the vapor phase, and we want it to occur at the initial temperature. Multiply it by the difference in the volume, so our volume total minus, and then in order to get the volume of the water, we need to use our density formula. So we have the mass of the water, which is our water, divided by, and then in order to get density from our file here, we'll just, it's P dot roll, and then we also want that at the initial temperature. And then we're going to divide all of that by gas constant times initial temperature. Okay, let's see if that worked. P is not defined. Oh, maybe that's because I had this as a capital P. Let's try that. Okay. That's better. Alright, sweet. So now that we've got that in there, why is there not a, there we go. Now all we have to do is define our function that we want to use then the root function in Colab to solve for when the function goes to 0, and then we can get our final temperature. So we're going to define our function here. Let's just call it pressure equation at, and then we're going to just do x, right? And then we want it to be the final temperature, and we want it to give us the first value in the list. Oops. Okay. And then we'll put in our volumes. The volume that we had up in this previous equation, volume in the vapor phase equals the total volume minus, and then we'll have our water divided by, and then we want this at the final temperature. Okay. Next, we will have the pressure of the water, pressure in and that is going to equal pressure. We just need a new variable because we're going to do the sum of the partial pressures, and we want that to go to 0. We'll have the partial pressure of the water, partial pressure of the air minus the final pressure, and that's what we want to go to 0. So we'll call this PWP in the vapor phase. We're getting this property from our files over here. And we want that at the final temperature instead of the initial temperature. Partial pressure of the air equals number of moles air times, this is just the ideal gas law, PV equals nRT. So R times, but we want the final temperature this time, which is what we're trying to solve for, divided by the volume in the vapor phase. And then lastly, we just want it to return the sum of the partial pressures, which is what should go to 0. So let's see if that worked. Awesome, we got that in there now. So let's add. We want to use our root function now to get when the function goes to 0. So up here, actually, I'm going to import, we're going to do from, that we're doing the SciPy, optimize, and import. We want to do the root function. Load that in there. Awesome. And then down here, we will do our root of our pressure equation at the initial temperature, which is what we know, and hopefully it will give us final temperature. So no. Props object has no attribute VAP. Oh, I keep doing capital V, right? There's no VAP. Oh, I forgot to put a P here. The pressure in the vapor phase. Sorry, not just VAP. Okay, maybe that'll work. Yay! Alright. Awesome. The solution converged. So here we go. This is what we got. And the X value, first X value is 366.33. So that is our final temperature when using the ideal gas law to raise the pressure of our closed system. So yeah. So now let's do one more example where we're solving for two unknowns instead of just one. So essentially, same calculation, same central concepts and formula, except now we have two unknowns. We don't know the final temperature and we don't know the volume of the whole container. We do know, however, that the number of moles of water in the vapor phase is supposed to be 0.3 moles. Everything else is the same. We want to get to 200,000 as our final pressure, but we need to solve for the volume and the final temperature needed. So essentially, two unknowns, we need to create two equations. So the biggest first step is we need to apply the number of moles of water, because this is our new parameter, so we have to use it. So we want to create a formula to calculate the volume given the moles of water. So in order to do that, the first thing we need to do is we need to subtract the moles of water. We need to get this into a unit that we can use. So we're going to convert from moles to kilograms so that we can get the volume. Because we know the mass of the water and we just need the volume of the whole container. So we're going to have our 0.3 moles times the molar mass of water are 18 grams per mole. And then we need to subtract the moles of the water, which is the 1 kilogram. I'm just going to write moles of water since we're just writing it like that, because that's the initial mass of the water. Okay, so then the volume is the total volume minus the volume of the water, or the liquid phase. So now that we have this set up, we know what the volume of the water is because we can just use our density formula like we did last time. So I draw that over here. The water is because we can just use our density, but now we need to apply the fact that we want 0.3 moles of water in the vapor phase. So in the end, we're going to have the volume of the water equals the mass minus this 0.3 all divided by the 1,000, 1 kilogram, 1,000 grams. And then we're going to divide it by the density to get the volume because we still have our volume. It's massive. We have our density is mass over volume, which means volume is mass density. So we're going to do the density. And it's going to be just like that. Okay? And we want to evaluate this given the parameters that we have. So we're going to end up using the final temperature that we got from the last problem to calculate the volume of the vapor phase, or volume of the water. So now we still need to get our equation for the partial pressure of the air and the water vapor. So we have this we can calculate in our Colab because we know all of these numbers. That'll give us the volume of the water. Now we want to do the pressure of the air, number of moles of air times RT. We're doing the final temperature this time divided by the volume in the vapor phase. Just dividing by the volume from the ideal gas law equation. Okay? And then we need our second equation because we have two unknowns. So we have the number of moles of water, we'll just write it as a W, in the vapor phase, which is our 0.3. We want it to equal, moving that over, pressure times vapor divided by RT. Okay, awesome. So these are, this is the final temperature of, because we're gonna evaluate everything at the final temperature that we got from the last equation, because that's gonna be our educated guess for what we think the final temperature of this will be, which I'll explain here in a second. Because in order to evaluate equations in Colab with using the root function, we need to provide an initial guess for what we think the solution will be. So for the temperature, we can use the final temperature that we got from the last problem because that should be a pretty good initial guess. But to guess for the volume, we can just use our equation that we have over here, which is the PV and RT using our 0.3. So the volume is going to equal 0.3, and we have the final temperature from the last problem times R times TF divided by the pressure. So that's essentially everything we need to solve the system of equations. I'll go over it more in Colab when we do the code, but the guessing is kind of the only part that makes this a little tricky, because sometimes when you're solving things in code, it's hard to know if it's your guesses that are off or if there's an error in your code. So this way, once we solved a simpler problem before where there was only one unknown, and now we can do a more complicated problem because we have those initial guesses from the other problem. So that's often a good trick. You can solve a simpler problem first in order to get good initial guesses. So yeah, we're going to plug these equations in and see what we get. So now we want to do one more example where we have two equations and two unknowns, and we still use the root function though to solve the system of equations. We do have one new parameter we need to put in here, which is the moles of water. I'm just going to write Wn is 0.3. So we want to put that in there, and then we want to make a new function. So we'll call this PEQ2, pressure equation 2, and we will also do that at x, just like that. And then we'll have our final temperature list here, or array, whatever, x0, and then the volume, total volume, which we don't know, is 1. Okay. So then we want to put in our formula for the volume at the vapor phase, and that is the difference of the two volumes. So we have our total volume minus, but this time we have to account for the number of moles of water that we have given to us. So we do the original water, which was the 1 kilogram, minus, but we can't just put in 0.3 because that's the moles of water, so we have to multiply it by the molar mass, which is in W, I think. By the molecular weight, which is in here, in the water properties. Where did it just go? Water properties, right here. And then we will divide that all by 1,000. And then we need to divide it by the density at the final temperature. So now that we have that in there, we still have to do the sum of the partial pressures. So we're going to do the partial pressure of the water equals our P dot pressure in the vapor phase at the final temperature. Partial pressure of the air is just our PV equals nRT. At the final temperature. And then we will have, now we need to make a new variable for the number of moles of water in the vapor phase. So we'll just call it the water vape. And this is also just our P, because we have our pressure in the pressure in the vapor phase multiplied by the volume divided by R times TF. Actually, I think I did this one. This is supposed to be divided by, I did this one totally wrong. Yeah, sorry, I was moving too fast. This is the PV equals nRT. There we go. And then this one is the number of moles equals PV divided by RT. And then we want it to return, the functions that we want to go to 0 are the sum of the partial pressures. So we have our partial pressure of water plus pressure of air minus final pressure. And then we also want the change in moles to go to 0. So we have our W vape minus Wn, which was our 0.3. Okay. Awesome, that loaded in correctly. Now let's see what it gives us. We will root. For this one though, we have to put in initial guesses for what we think the values are going to be. Since we solved the other problem, we have a pretty good idea of what we think it will be. We have our 366 from our last problem for the final temperature, so we can go ahead and put that in because it should be pretty close to 366. And then for the volume, we had 0.01 meters cubed, so we're going to go ahead and put that in too and see what we get. See if the system converges. It takes one positional area, but two were given. Oh, I think I needed parentheses here. Name TF is not defined. Huh? Let's see. Oh, I forgot to put an equal sign. Let's try that. TF is not defined. Why is TF not defined? Oh, I didn't put X's here. Sorry. Let's try that. Okay. Yay! Okay, let's see what it says. The solution converged. Awesome! So now we have our two values down here for the temperature and the volume, and we were able to correctly use our ideal gas law to create a system of equations where we have two unknowns, two equations, and put it into this code and make a function. So it's pretty cool.